Hi, I'm Goli Mohammadi, Senior Editor of Make. In the latest Weekend Project, we'll be taking a look at you. Well, specifically, your pulse. Taking your pulse is as simple as holding a finger to your neck or wrist and timing the beats with your watch. But if you want to monitor your pulse over a period of time, you'll need a way to turn that mechanical action into an electrical signal. In this project, we'll build a sensor that fits over your fingertip and reads the amount of infrared light reflected by the blood circulating inside your body. You can do a lot of fun things with this sensor, but it's not a medical device. If you really need to know your heart rate, go see a doctor, not your local makerspace. When your heart pumps, blood pressure rises sharply, and so does the amount of infrared light from the emitter that gets reflected back to the detector. The detector passes more current when it receives more light, which in turn causes a voltage drop. This design uses two consecutive operational amplifiers, or op-amps, to establish a steady baseline for the signal, emphasize the peaks, and filter out the noise. Both op-amps are contained in a single integrated circuit, or chip, so hooking them up is just a matter of connecting the pins correctly and reading the signals with your Arduino. The first op-amp amplifies the signal and passes along to the second op-amp, which outputs a clean but still weak signal, which is finally amplified by the transistor before being sent to the Arduino. You don't need a lot of parts to make this project, and all of them are available at your local Radio Shack. So with one quick trip, you'll be ready to build this project. You'll also need the following tools. The completed sensor is a 3-wire device that outputs the pulse signal on the white wire. You can visualize or record this signal in a number of ways. We have decided to connect to a personal computer through an Arduino. Let's start by cutting down the perf board to size. The PCB pattern is not symmetrical, so be sure you're removing the correct side of the board. Double check before you cut. Score the board using a straight edge and utility knife, then snap it away from the score line along a table edge. The cable clip is used as a finger cuff to hold the pulse sensor against your skin. Drill 2 holes in it for the emitter and detector to poke through. Now we need to mount the emitter and detector. The emitter has a purple hue, while the detector is clear. Align them flat to flat and pass their leads through the PCB, placing the emitter closest to the end of the board. Bend both ground leads over and solder them to the nearest rail. Attach 2 resistors between the power rail and the remaining emitter and detector leads. The emitter gets a 220 ohm resistor and the detector a 39 kilo ohm resistor. The LM324IC contains 4 identical op-amps. Our design only uses 2 of them. To avoid making accidental connections, clip off the bottom 3 leads on each side of the chip. Solder the chip's pins on the bottom of the board. Provide power and ground connections by flowing solder between pins 4 and 11 and the rails adjacent to each. Now let's wire up the op-amp. First, solder the 2 0.1 microfarad ceramic disc capacitors. The first goes between pins 1 and 2, and the second between pins 13 and 14. Mount and solder the remaining 6 resistors according to the schematic. Mount the 2 tantalum electrolytic capacitors. These are polarized components, so make sure you insert them properly. In each case, the negative lead should be connected to the chip. Make sure to extend connections out from each pin along each row to connect all the components. Finally, install the NPN transistor as shown, making sure it's oriented correctly, with the emitter lead next to the PCB edge and the 1.8 kilo ohm resistor lead connected to the middle or base pin. Now we'll make final connections on the solder side of the board. Start with 2 insulated jumper wires. One connects the photodetector to the primary op-amp input, and the other connects the primary's output to the secondary stage input. Each is connected at one end to the positive lead of one of the tantalum capacitors. Add 2 short insulated jumper wires to bring power and ground across the chip. The red jumper connects the transistor collector to the power rail. The black jumper connects the primary stage resistors to the ground rail. Now we need to connect the signal to the Arduino. We can make our own cable by cutting a length of 4-wire intercom cable. The pulse sensor only needs 3 conductors: power, red, ground, black, and signal, white. So peel off the outer green wire and save it for another project. Now you can remove the adhesive film from the base of the cable clip and fix it to the component side of the PCB over the emitter and detector. Your sensor is now ready to use with the data recorder of your choice. We love Arduino, so we'll use it to set up a serial connection to processing and perform some interesting visualizations. To connect the sensor to your Arduino, insert the black lead into the pin marked ground on your Arduino, the white signal lead into the header marked A0, and the red lead into the pin header marked 5 volt. You can find basic Arduino instructions and the simple serial reporter Arduino sketch from the link on the project page. Next, open it in the Arduino IDE and click the arrow button to upload the sketch to the Arduino. Now, open the Arduino software serial monitor tool and you should see the raw data streaming from the sensor as a column of numbers. The simple serial reporter sketch reads values from pin A0 and passes them down the USB cable to your computer. Now let's turn that data into a graph. Download the visualization sketch and the latest version of processing from the link found on the project page and open it. Simply click the triangle button to run the code. Flip the cable clip over your thumb or finger and watch the rhythm of your pulse. Now that you can measure and see your pulse, think about all the fun you can have. Does your heart rate increase when you tell a lie or laugh? Try making a truth detector or control the speed of a motor based on your heart rate. It's all fairly easy with an Arduino and your new pulse sensor.